We are Team 14 and today we'll be presenting a project and design for manufacturing and assembly for a blender. Our focus has been to analyze the product's design, identify inefficiencies and propose practical improvements to enhance manufacturability, assembly and cost effectiveness. Blender is a versatile kitchen tool used for blending, pureeing and emulsifying. Its advantages include time saving, nutrient retention, portability and ease of cleaning, making it indispensable for health conscious and busy users. Our blender targets amateur fitness enthusiasts and busy individuals seeking quick meal preparation. It also caters to home user blending smoothies, soups, and sauces. Annual production exceeds 100,000 units, scaling to meet demand. The blender consists of 21 components including casing, motor, button assembly, and blade shaft. This breakdown informed our redesign efforts focusing on parts impacting assembly time and cost the most. Fast diagram identifies key functions of the blender, showing areas for improvement. For example, the button assembly and the blade shaft emerged as critical components for redesign, balancing functionality and manufacturability. Function component mapping matrix helps align components with their functional importance. High priority components such as blade, button assembly, and the blade shaft were targeted for redesign to enhance efficiency. Cost analysis of materials revealed opportunities for cost reduction. By redesigning components like the button assembly and blade shaft, we achieved significant material and assembly cost savings. Quad chart for DfM shows parts categorized by functional importance and manufacturing or assembly cost. Parts like the button assembly and outer casing stood out as ideal candidates for improvement. Family design uses a common platform of the casing assembly, blade shaft, and button assembly. This ensures manufacturing efficiency while modular customization meets specific customer needs, achieving our goal of balancing flexibility and cost effectiveness. Our analysis revealed inefficiencies in manual and automated assembly sequences. By redesigning high impact components, we streamlined processes, reducing time and enhancing manufacturability.
This slide presents the manual assembly time before redesign totaling 166.35 seconds with a current assembly efficiency of 45.87%. For platform selection, we have chosen the lower casing, upper casing and handle to optimize the structural foundation. For module selection, we have focused on blade and blade shaft to streamline functionality. These targeted changes aim to simplify the assembly process and enhance efficiency. This slide represents the functional component matrix showing the role of each component in the assembly. The lower and upper casings, lower middle casing and handle have been redesigned to reduce noise and facilitate handling, enhancing performance while simplifying assembly. Additionally, the blade and blade shaft share the function of facilitating cleaning. Through the redesign, we have reduced the number of parts while maintaining functionality, resulting in a more streamlined and efficient assembly process. The new redesigned parts have reduced the manual assembly time from 166.35 seconds to 132.7 seconds, improving efficiency by 12.32%. This significant reduction is primarily due to the elimination of two fasteners, lower middle casing and handle, which streamlines the assembly process and boosts overall productivity. The table on the right highlights the differences between the original and the new design, demonstrating how these changes led to more efficient and cost-effective assembly process. In this redesign, several DFM principles were applied to improve assembly efficiency. Two fasteners were eliminated, reducing the assembly time and complexity. The handle and lower middle casing were eliminated, reducing the number of parts. Snap fit connections were introduced for the casing, simplifying attachment. Symmetry was achieved in upper and lower casing, improving handling. Hand and tool access was optimized for the blade and blade shaft, enhancing ease of assembly. While this requires an initial investment, the overall production costs are reduced over time due to the improved assembly efficiency, making the process more cost effective in the long run.
So talking about the automated assembly, integrating the button cover and the spring into a single assembly for automated assembly makes sense based on the functional component mapping matrix for the following reasons. Integrating those components into a single assembly offers significant benefits for automated assembly. These parts share multiple functional roles, making integration an ideal way to simplify the assembly processes. By reducing the number of components, we streamline the design, minimize assembly complexity, and improve throughput, ultimately driving down costs. This approach aligns perfectly with design for assembly principles, which aim to optimize designs for efficient automation. The results is a more reliable process with fewer errors, lower inventory needs, and improved overall production efficiency, making integration a smart and a cost-effective solution. Before integrating the button cover and the spring, the handling and the insertion cost per unit was $45.845. By combining these components into a single assembly, we significantly reduce handling time and insertion complexity, as fewer components mean fewer operations for the automated systems. This integration streamlines the design, minimizes assembly steps, and supports faster throughput, aligning with design for assembly principles. The result is a noticeable reduction in costs and the more efficient error-proof processes, offering a strong return on investment for automation. After the integration, the cost has been reduced to $0.4032, representing a significant efficiency improvement with no major changes in the product functionality. While the initial manufacturing cost increased due to design and tooling investment for the integrated part, but the overall manufacturing cost decreased over time. This cost reduction is driven by fewer components, simplified assembly, and improved automation efficiency, making the integration a cost-effective and functionally sound solution.
Let's delve into the DfM Pro recommendations for using injection molding on the initial components we assessed for redesign to cut costs and reduce the number of parts. These components are part of manual assembly, which include the upper casing, middle casing, lower casing, and handle. DfM Pro software recommend enhancements such as minimum radius at the base of the pass, minimum draft angle, uniform wall thickness, mold wall thickness, and rib parameters. By implementing these suggestions, the total manufacturing cost for these parts came to $5.525. By following the DfM Pro recommendations, these are the redesigned parts where we have streamlined the casing into just two components. We adhere to the DfM Pro recommendations for injection molding, resulting in a significant cost reduction compared to the original parts. The redesigned casing features fewer snap widths and a reduced number of parts, which translates to decreased assembly time and improved tool accessibility. Consequently, the manufacturing cost has been reduced to $1.496. Additionally, we have evaluated another component for manual assembly, the blade shaft. The DfM Pro recommendations for this part include rib parameters, minimum draft angle, and mold wall thickness. Following these suggestions, the manufacturing cost for the blade shaft is estimated to be $0.768. Following the DfM Pro recommendations, we have added a threading at the end of the blade shaft with a thread size of metric 1.2 by 0.25. This is where the blade can directly fix into it without the need of any extra bolts or screws. By this method, we have reduced the assembly time and reduced the cost for the assembly, where it is coming to be $0.608.
Our primary redesign efforts were on the button cover and the spring, where we eliminated the standalone button by integrating its functionality into the spring, as shown in the slide. The total manufacturing cost for these redesigned parts is $1.8. The redesign was guided by DfM Pro recommendations, including ensuring a minimum draft angle, maintaining uniform wall thickness, optimizing rib parameters, and minimizing undercuts. These improvements help streamline manufacturing while reducing costs. Integrated the button functionality into the back of the spring and redesigned the button cover to optimize its features. While the redesign aligns with most of the DfM Pro recommendations, we were unable to completely eliminate two minimum draft angles and undercut detections. However, we successfully addressed the most critical and high priority recommendations for the button cover. This redesign has also reduced the manufacturing cost to $1.69. Enrich customer experience and address environmental concerns, we propose a product service system. This approach integrates product functionality while tailored services such as repair and upgrade programs, take back initiatives for recycling and refurbishment, and subscription based services for part replacement and maintenance. Designing for ease, disassembly, and recyclability, promote sustainability, and aligns with a circular economy, reducing waste while maximizing customer satisfaction and product longevity. Thus, the redesign of the blender focuses on achieving customer convenience, sustainability, and efficient manufacturing by adopting modular designs. We reduce manufacturing cost and assembly complexities while enhancing functionality and repairability through sustainable practices such as material optimization and ease of assembly. The product support eco-friendly solution and meets current environmental expectations. Additionally, the incorporation of service-based system ensures prolonged product life, increasing customer satisfaction and fostering loyalty. Thank you so much.